In this video, we're going to talk about the Russian-designed block cipher called Kuznyechik. It's a 128-bit block cipher that uses a 256-bit key. In this video, we're going to be implementing the Kuznyechik block cipher. In this document here, it's a specification for, in fact, two different block ciphers, and we'll implement both. In this video, we'll implement a Kuznyechik block cipher, and in the next video, we'll implement the Magma block cipher. And you can see that right here. This is the Kuznyechik block cipher. It's a 128-bit block cipher, and it has a 256-bit key. We can copy all of that and put it into Google Translate. So we see that this standard, it describes two basic block ciphers, one with 128 bits and one with 64 bits. The 128-bit block cipher is called Kuznyechik, and that's the one we're going to be implementing in this video. And the 64-bit block cipher, that's called Magma. This GHOST, G-O-S-T, is like NIST for the US. And I also wanted to show you this reference here. This is the English translation of that. And you can find that at this link. One thing to notice is that Kuznyechik means grasshopper. So where do we start to program this? Well, let's start here. First is this S-box here. It's an 8-bit S-box, and it's defined by this list. Just paste in the definition of the S-box that's given there. Now we also need the inverse of this, and the inverse is actually not specified in this document, but it is specified in this one. So pi inverse is right here. We're going to need that as well. We can paste that in. Now the first function I would like to implement is this function s here. If we're given a 128-bit value a, we imagine it as 16 bytes. So 16 values, each having 8 bits each. And then we just apply the pi to each 8-bit sequence, which produces another 8-bit sequence, and then we concatenate all that together to make a 128-bit sequence. So to implement that, let's see how that goes. So we imagine the function s has an input of 128 bits. We're going to call y our output, and it starts off initialized at 0. Notice how we're doing a reversed range here. So we're going from 15 down to 0. The very first cycle of the loop, when the I is 15, we shift X over by 120 positions. And that exposes the 8 most significant bits of X. And we AND it with 0xFF, which is just 8 ones. And that grabs the most significant 8 bits of X. And we feed that into the S-box pi. And then we adjoin that to the value of Y. In each cycle of the loop, we shift y over by 8 spots, and then we add on the next value of pi through the next chunk of 8 bits of x. And that's how we construct the value of y. So that defines the function s. And if we look in our document here, and we look at the end, they actually give us some values that we can test to see if things are working or not. So why don't we just do a quick little test there. And so when we run this, we see that we get this value, and we can compare that to the value that we should be getting. And we see that they are the same. So it looks like that's working. We're also going to need the S inverse function, which is really exactly the same thing, except that we use the pi inverse list instead, right? And we can test that that's working just by applying S inverse to this. And we'll make sure we get back to that original value. And we do. So our functions S and S inverse are working. Now, to move on to the next part, we actually need to use some code that I wrote in a previous video called the Rindall S-box. And for that, we can go to my GitHub page. And located at this address here is some code I wrote for the video on constructing the S-box of the Rindall cipher. And we're going to need a few of these functions here. We'll just copy the first 4 functions, which are called multiply ints as polynomials, number of bits, mod int as polynomial, and Rindall multiplication. We're going to copy those and paste them in here. So the first function here, which we pasted just under S inverse, is multiplying the ints as polynomials. And I don't want to spend too much time explaining this because all the detail is in that other video. But basically, this takes 2 non-negative integers. It looks at their binary expansions and then associates polynomials to them whose coefficients are either 0 or 1. It multiplies those polynomials, and then that's associated to a binary value, and which is an integer, and that's what this calculates. And the next little function we need is just the number of bits that are stored for a non-negative integer x, and the minimal number of bits. And then we want to write a little function to mod an integer as if it were a polynomial. So imagine x is an integer and m is another integer. Each of these has bit expansions and can be interpreted as binary polynomials. We can mod the polynomial x by the polynomial m, and we get a new polynomial back, and that has a binary expansion, which is an integer, and that's what this returns. Now in the Rindall multiplication, we multiply, the way we proceed with multiplication here is we multiply these integers as if they were polynomials, and then we mod it out by this polynomial here. They actually use a different one, and that'll be over here. So here's the polynomial they use, which is different, right? Degree 8, so that'd be a 1, but then they have a degree 7 as well, and a degree 6, and then no degree 5, 4, 3, 2, and then a degree 1 and a constant term of 1. So 876, 876, and then zeros everywhere else. So that's degree 8, degree 7, degree 6, 5, 4, 3, 2, and then there's your x, and there's a 1. So this should be changed from Rindall multiplication to Kuznyechik. So this is Kuznyechik multiplication instead of Rindall multiplication. And because we're modding out by a different polynomial than the Rindall construction. So that's good. Every time we have 2 8-bit integers, we can multiply them with this new type of multiplication and get another 8-bit integer back. The next function we have to write is the Kuznyechik linear functional. Its specification is found over here. We take a 128-bit value x and we imagine it as a vector with 16 positions, and in each position is a byte, something like this here. This value of c here is written as a vector of 16 integers, and each integer is a byte. It's between 0 and 255. The way we access these 8-bit segments of this 128-bit value is like this. We AND it with FF, which is 8 ones, and that grabs the 8 least significant bits of x, and then we cycle x to the right by 8 for the next cycle of the loop. And then we grab the next 8 least significant bits. And each time we grab a byte of X, there's 16 in all to grab. We take off the last element of this list and we multiply it together using the Kuznyechik multiplication. And we add that on the current value of Y. And this is really a linear functional where the field is the set of bytes under the field structure given by the Kuznyechik multiplication. And this really goes from the 16-dimensional vector space over F to F, and that's why it's called a linear functional. The next function we have to define is R. And the way we define R, it's given over here in the specification. We take in 128-bit input, and we apply the Kuznyechik linear functional to the input. We get an 8-bit value back, and that becomes the new most significant bit of our value. Notice we shift that over by 15 positions to get it in the most significant spot. And then all the bit values of X are shifted to the right by 8. That's what's going on there. And we can test this out. They do give us some test values for R here. So why don't we try this? Let's take X to be this value here, and we'll see if we get the proper value that we're supposed to. So it's 9, 4 at the beginning, and all zeros, and then a 1 at the end. And that's what we see over here as well, right? 9, 4, all zeros, and then a 1. So it looks like our R value is working there. And the next function after R is L. And L is easy because L is just R composed with itself 16 times. So we can just copy that in. To find L, we take in 128-bit input, run that value through R 16 times. The reason I use this little symbol, I could use the letter I here, that'd be fine too, but since I doesn't play a role in the loop, I think a common convention is just to use the underscore to indicate that the variable, even though this is a variable name, this is done to indicate that the variable name doesn't matter in the loop. And we can test that out as well. We saw a sample value of L here. So if we take in this value of L as X, and then we pass that into L, do we get what we want? So it looks like at the front we got D45, and at the end we have 90D. And when we compare that, D45, 90D. So I think we're good on L. And now we need to do the inverse of those functions. R inverse is given right here. And the specification for R inverse is given in the over here. So we take in 128-bit value. We imagine it as 16 bytes. We grab the most significant 8 bits, and then we shift all the values, all the bits of X to the left by 8. But by doing that, we're going past 128 bits. So by doing this little trick here, we mask off only 128 bits. This sets to 0 any bits that are past 128. We really adjoin these. We do X, XOR A, which just glues these together kind of to make a 128-bit value. But for now, that's good enough for implementing that. And for L inverse, just as L was R done 16 times, L inverse is going to be R inverse done 16 times. So that's easy. The next thing we have to do is implement the key schedule for the block cipher Kuznyechik. The specification is located right here, and here's the code for it. So we take in a 256-bit key, and the purpose of the key schedule is to produce 10 keys of 128 bits each from that 256-bit key. And these 10 keys will be used in the 10 rounds of the encryption function. So the specification there, it uses these constants. And the way we find these constants is we just take the integers from 1 to 32 and we put them into the L function. And we can see that going on right here. As I goes from 0 to 3 and j goes from 0 to 7, this quantity here, a times I plus j plus 1, goes from 1 to 32. And then we get that constant c there that's specified in the documentation here. So notice the first thing they do there is define the keys K1 and K2. And the way we get those keys is just by taking the left half and the right half of the 256-bit key that's given to us. That's how we get our first two keys of 128 bits each. So we append those keys onto our list right there. And then we have 8 more keys to go. And in each round on the I, we produce 2 more keys. And we can see these 2 keys being defined here as a tuple. Notice it's defined by taking the previous 2 keys and then feeding them into this F function. And that function's defined up here. And instead of writing it like that, I just coded it in directly. It's the same thing. When you look at the definition of F here, you see how this function F is just coded directly here. The L is there, the S is there, and then we have an XOR, and that's present right there, except the XOR is with the constant value C, right? We cycle through that loop 8 times to change the values of A and B, and then we add those values of A and B to our list of keys. And we do that 4 times, and that generates 8 more keys. With these 2 initial ones, that gives us a total of 10 keys. And we can test this. There is some test values given in the document here for the key schedule. Here's a 256-bit key that's given to us. And then we can call our key schedule on that. And then we can just print off all the keys. And we can compare those to the keys that we're supposed to be getting. Here they are. K1, 8899. K2, FED. Notice how that corresponds to the left half of this. That's K1, right? And then K2 is the right half of the original key. That's how we define K1 and K2. And then the remaining ones, K3 through K10, are defined with the algorithm there. And we can see that everything's matching up here. Our last key is matching, and looks like we're in good shape for our key schedule algorithm. So that's good. Let's erase this, but we'll keep our key for later. And now we're finally ready to implement the encryption function. We can find the specification for the encryption function over here, just after the key schedule. And notice that we take an input A, which is 128 bits, and we apply an XOR with the first key in the key schedule, and then S, and then L. And then we repeat that. We take the XOR with the next key in the key schedule, and then the function S, and then the function L, and we do that 9 times. And then at the very end, we just XOR it with the last key in the list. And that's how the encryption function for Kuznyechik works. So that'll be very easy to code. It'll just be this, right? We take our 128 bits block in for input to encrypt. That's our plain text. And we have a 256-bit key. We first call the key schedule on our key. That produces a list of 10 128-bit keys. We do 9 rounds. Each time we take our value of X and we XOR it with the round key. We feed that into S, and then we feed that into L, and we redefine X that way. And then on the last round, which is the 10th round, we just do an XOR with the last key in the list. That's what that -1 notation means. And that's the encryption function for this block cipher. So we can test that. We have some test values here. So this is a 128-bit value here that we're going to encrypt. Why don't we call that plaintext PT? And our key is defined before there. And then our ciphertext should be what results from the encryption function, right? So we take our Kuznyechik encrypt function and apply it to the plaintext with the given key. And what we're hoping for is that this ciphertext is the value that they're going to give us. So let's try that. So we get this quantity. Let's see if that matches what the expected encrypted value is. There we go, 7F6, 7F6, ending in DCD. So that looks good. So we apply 10 rounds, and we go from the plaintext to the ciphertext. So that's working. And now we should go the opposite way. We should take this ciphertext, which is right here, and then feed that into the decryption function, and we should recover the original plaintext, which is right back up here. So let's see if that's going to work for us. Why don't we look at the decryption function? The specification for that is back up here. It's really pretty much the same as the encryption function, except of course we're using these functions L inverse and S inverse. And also notice the keys are used in the opposite order. We start with the 10th key and then we work our way down to the first key. And again, notice in the last round how we just do an XOR. We don't have any S inverse or L inverse on the 10th round. So we can implement that, no problem. It's basically the same code, right? Except we're just going to have to remember to reverse the list, which is done right there. And the difference there, of course, like we said, is instead of S and L, we're using S inverse and L inverse. And notice they're in the opposite order here, right? Then the L and the S were over here. But other than that, it's quite similar. And now we can test if this decryption function is working. Because what we can do is we can call DT to be the decrypted text. So let's call the decryption function on the ciphertext using the same key. And what we are hoping for is that the plaintext, original text, is equal to the decrypted text. And if that works, then we've successfully implemented this cipher. And we get a true. So we're good. So we've implemented the Kuznyechik block cipher. We can encrypt and decrypt 128-bit blocks with a given 256-bit key. Before I end the video, I just wanted to make a few more remarks on the Kuznyechik linear functional. Why don't we let F2 be the field of two elements, so it only contains 0 and 1, and T will be an indeterminate variable, and F2T will denote the polynomial ring. And our polynomial there that we saw, this 8th degree polynomial, is irreducible. And so if we look at the principal ideal generated by it and mod the polynomial ring by that principal ideal, we in fact get a field. And the cardinality is 2 to the 8. And the set of polynomials of degree less than 8 in the polynomial ring F2 of T is in fact a complete set of coset representatives for that quotient. And any polynomial of degree less than 8 is having 8 independent coefficients, and each of them are bits. And in this way, we identify elements of F with 8-bit sequences. And 8-bit sequences are bytes, which are in bijection with the integers from 0 to 255. So that's just a very rough explanation of why we can identify elements of F, which are technically speaking cosets of polynomials, with plain old integers from 0 to 255. So when we write bold F, we imagine we're dealing with integers between 0 to 255. The addition operation is XOR, and the multiplication operation is this Kuznyechik multiplication that we implemented. And F under this addition and multiplication is a field. And just like with any field, we can do linear algebra over that field. And a linear functional is just a linear map from a vector space to the field itself. So in particular, the vector space that we're using here is just F16. So it's a 16-dimensional vector space over F. And any linear functional really comes from a dot product. And so a linear functional from F16 to F, which is associated to a fixed vector C in F16, how does it act on a typical element X? It just sends X to the dot product of X and C. And that dot product in this case is defined as the XOR summation from 1 to 16 of Xi times Ci, where the multiplication, of course, is this Kuznyechik multiplication that we've defined. And the addition symbol here is XOR. The Kuznyechik linear functional is defined with respect to this particular fixed vector C that's given right here. It's an element of F16. And I just wanted to point out that this while loop is in fact implementing the dot product. And then the last thing I wanted to make some remarks on was the R function that we find in this paper. The definition of R, as we saw in the specification, is given here. And they also gave the function R inverse there. And notice both of these functions are defined with respect to the Kuznyechik linear functional L that we talked about. Now, when I first looked at this, I wasn't completely clear about why is it true that R inverse composed with R is the identity. So why don't we just run through the details of seeing why that's true. So let's unravel the definitions here. R inverse composed with R acting at X, just by definition, is R inverse evaluated at R of X. The definition of R of X there is L of X comma X1 up to X15. And how does R inverse act on that vector? Well, it shifts everything over to get X1 to X15 as at the front. And then here's where the expression looks a little bit weird. We got to evaluate L at the vector X1 up to X15. And then the last position is L of X. So for this map to be the identity, we need that the value here be X1 up to X16. We see everything matching up on X1 up to X15. That's no problem. It's just that last coordinate. The question is, why is that last coordinate there equal to X16? So in other words, why is it true that L of X1 up to X15 comma L of X why does L evaluated at that 16 component vector give you X16? So we can work that out over here. Well, the definition of L evaluated at any vector is you just run through the summation, the XOR summation, with the individual bytes multiplied by those constants Ci. So that's what we're doing here. For the first 15 variables, we're just using Xi. And then the last one, it's L of X. But we do run through all of the constants C1 up to C16 there. Now, if we just focus on that first part there, the summation from 1 to 15 of Xi times Ci is pretty much L of X, right? The only thing it's missing is the last term, which is C16 times X16. So in some sense, that expression in brackets there is L of X minus C16 times X16. But for XOR, minus is the same as plus. So we can replace that expression in brackets there by L of x plus C16 times x16. Now here's the point I want to make for the vector C that's used in the Kuznyechik linear functional. It is the case that the last term C16 is equal to 1. And when we use that fact that C16 is equal to 1 and put that in that equation, we find that we get L of x plus x16 plus L of x, right? Because the C16 being 1 makes the multiplication trivial, and we just get the variable x16 in the first bracket, and then we just get L of x there in the second bracket. And what do we find? We have L of x plus x16 plus L of x. And we know that when we XOR two of the same value together, we just get 0. So the L of x plus L of x just cancel out. And the only thing that's left is x16, and that's what we're required to prove. So I just thought that was quite nice, and I wanted to run through that calculation. So notice that it's important that in the implementation here that C16 would be equal to 1. That's important in order for the formula for R inverse there to be, in fact, the inverse function of R. All right, that completes our discussion of the Kuznyechik block cipher. Thanks for watching.